Hi. Today we're going to begin a three-part study on graphing the sine, cosine, and tangent functions. Today what we're going to do is establish what the graphs of sine, cosine, and tangent look like. The next lesson will be transforming them, and then finally we will be curve fitting, that is taking a situation and finding a sinusoidal function or a sine function that fits that pattern. But today we're going to start with sine, cosine, and tangent, and all of those are cyclic or periodic functions. That is, they repeat endlessly forever and ever. The x interval that it takes for a full cycle to go by is called the period of the function. And you can see that my table is in radians, but I'm not going to let that bother me because by now you and I both are familiar to transferring to degrees, which we're more familiar with. Pi 6 is 30 degrees, pi fourths is 45, pi thirds is 60, pi halves is 90, and you can see a jump of 30, then 15, 15, and 30. So this would be 30, the jump of 30. 15 would get you to 135, 15 would get you to 150, and 30 would get you to 180. And we could continue going on, but I think that you've got the picture. I'm going to set my table up. See, now I have my function in y equals sine of x. I want to set up a table so that I can get some estimated values to plot here. And I do want it to start at 0. I'm going to ask it to go up by 15s, however. I know that I'm going to have some table values that I don't use, but that's all right. And you can see from here that the sine function when x is 0 is 0. The first angle measure that I'm interested in is 30 degrees, and the sine there is 0.5. At 45 degrees, it's roughly 0.71. At 60 degrees, it's 8.7 about, or 0.87. At pi halves, the sine is 1. And I'm going to go ahead and do this one, and I'll show you the rest of this, but then I'm going to say we can use our head on this and be a little bit smarter than our calculator maybe. I'm not interested in 105, but I do want 120, and I see that it repeats that 0.87, and I think to myself, you know, I know what this graph is going to do. It goes up, and then it comes back down the same way. So at 3 pi over 4, the y value should be around 0.71. At 150 degrees, we're at 0.5, and at 180, we're back to 0. Now, from there, I'm pretty sure you know what happens. We've done an up cycle. Next comes a down. And at 7 pi over 6, which is 210 degrees, we are at negative 0.5. And so now we're on our downhill track. Negative 0.71, negative 0.87, negative 1 at 3 pi over 2. That's straight up and down. Negative 1 is the sign there. Then we start climbing again. Negative 0.87, negative 0.71, negative 0.5, and back to 0. All right. So what I'd like us to do is just plot one cycle of this. And the graph paper that I put on your notes, each of the increments here is a half pi. And we go from in the y direction from 2 to negative 2. So we're going to start with one cycle of the sine, and at 0 the sine is 0. At 30 degrees, well, you know what, 30 degrees, this is a pi halves, that's 90, so that's like a third of the way through here. We're at 0.5, and then we jump to 0.7 and 0.8, and finally at pi halves we get up to 1. Then we start coming down, 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 and halfway, and then we're back to 0. And now that pattern is going to repeat itself here. A third of the way through, and then 15 and 15 until we reach the bottom, and then we turn around and start coming up, 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 up until we hear, and there's one full circle. or 1 full cycle. Whoops, I lost my inflection there. Alright, now I know that I could extend this because the sine is a periodic function, and if you look at the what I would call the high points, highs and lows here, to graph a cycle of sine, it's 0 to the maximum, 0 to the minimum, back to 0. Now if I kept going this way, I could add, and I'm going to change colors, so that cycle would repeat itself endlessly as long as we wanted to keep going. That wasn't very smooth. And so now we've got an idea of what the sine does. You can see that it starts at 0, the y-intercept is 0, it has x-intercepts that we'll want to talk about, it has maximums and minimums that occur at regular locations. Let's see if we can't just jot some of that down. Okay, the period for the sine function, all this data, by the way, is on page 360 in your textbook. The period is 2 pi radians. The y-intercept for the sine is at 0, 0. X-intercepts, I'm going to, I'm going to refer back to my graph. X-intercepts happen at 0, at pi, at 2 pi, it would happen again at 3 pi. It's multiples of pi where you find zeros for the sine. So they are at multiples of pi. And the way that we would write that is this. X equals 0 at pi n, where n is an integer. Just means any number that we put in for n, as long as it's a integer, we'll have an x at 0. X-intercepts happen at multiples of pi n. The domain for the sine function we've already talked about. It goes from negative infinity to infinity. That is, any value can be input as an angle measure. The range is more specific. The lowest it can be is -1, the highest is 1. Maximums occur at, so, okay, this is we're going to need to look at the graph again. Maximum for the sine function is when it hits 1. And you can see that it does that at pi halves. It's not going to hit at 1 again until it goes through another full cycle. That's 5 pi halves right there. That's a multiple of pi half. It's one full cycle past pi halves. So I think we could write it this way. Maximums happen at pi halves plus 2 pi n. Again, every full cycle after that. Minimums, well, the minimums in this function, -1, that happens at 3 pi halves in the first cycle and every 2 pi thereafter. So 3 pi halves plus 2 pi n. Alright, let's see if we can use that information to help us solve or answer these questions. We want the sine at 9 pi over 2. Okay, so I'm thinking to myself, I want to start taking away full turns until I get into the range that I'm familiar with. So I want to take away 2 pi, and 2 pi in halves is equal to 4 pi halves. Agree? So let's start taking away 4 pi halves at a time. We take it away once, we get to 5 pi halves. That's still bigger than a cycle. We take it away twice. That is 8 pi halves taken away. That means we're at pi over 2. And guess what? At pi over 2, it's at a maximum according to this, so the value is 1. Okay, and we found that by taking away full cycles. If we want to find the values of theta for which sine theta equals 0 is true, you guys, we have that right here. The values of theta which make the sine 0, that's x-intercepts, and that will happen at theta equals pi times n, where n is an integer. Good. To graph the sine of x over the interval negative 3 pi to pi, that is not going to be an issue for us either, because we know how to do this. We know that, and I'm gonna cheat. Okay, it's not really cheating. We know that a full period is 2 pi, and we know that in this curve, it has to have a full up and down in 2 pi radians. I'm going to go ahead and start marking other. So there's negative pi. There's negative 2 pi. Here's negative 3 pi, and that's where they want us to go. All right, so they want us to be from pi on top. Pi is where we're at 0. But if you think about what the curve is doing, from 0 to that interval, it starts there, it hits a high point, and so this is the pattern. Now we're down, now we're 0, now we're up, now we're 0, now we're down, and now we're back to 0. So graphing that sine curve over the interval that they asked us to do isn't difficult, as long as we can remember what the sine curve is doing at its various places. What I'm going to ask you to do is the same thing for the cosine of x, remembering that this is 30 degrees, 45, 60, 90, etc. And I will go ahead and write my table values in, and I will catch up with you when I have my table filled out. All right, here's my table all filled in. As you can see, the cosine function, when x is 0, y is 1. So this time we start up. Okay? We still can go, to graph this easily, we still can go in, if we think about what it's doing at the quarter points, at pi halves we're at 0, so we're max to 0. Pi we're at the minimum, negative 1. 3 pi halves we're back to 0, and 2 pi we've come full cycle. So here's one full cycle of the cosine. And if we wanted to extend in the other direction, we could still keep following that same trajectory backwards now. And there you have it. There's the cosine curve. The period for cosine is 2 pi as well. It has its y-intercept at 1. X-intercepts happen at, and you can see that it's pi halves and every pi beyond that. So it's pi halves plus every pi after that, pi n, where n is an integer. So if you're on a pi mark in cosine, or a pi halves mark, if you're on a pi halves mark, you're going to be at 0. The domain for this function is the same as for the sine, negative infinity to infinity. The range is the same, negative 1 to 1. It has maximums at every 2 pi. So 2 pi n, again where n is an integer, and minimums for this happen at pi and every 2 pi n after that. So pi plus 2 pi n. That's the cosine function. Starts at 1. So when I'm graphing this, I'm thinking max, 0, min, 0, max. That's the way to graph that cosine function. The last one that we're going to look at today is the tangent, and I will get my table going for tangent. Ask you to copy it down or make your own table. This time we know that the tangent function has a period of pi because we've seen that before. So by the time that we go through here, we will have done an entire period of the tangent. And here it comes. So we have one full cycle of our tangent right there. Let's graph what we have. 0 at pi 6, so a third of the way through, it's at 0.6. Half the way through, we are at 1. And at pi thirds, which is almost 2/3 of the way through, we're at 1.7. But then we have undefined. Folks, the tangent has asymptotes. It has vertical asymptote every multiple of pi halves. Every multiple of pi halves is an asymptote for this function. So we have part of it there, doing that. Here comes the rest of, I'm going to graph up through 2 pi, just following what we've got here. Negative pi halves were undefined, but at 2 pi thirds, we're at negative 1.7. So down here, then at 3 pi fourths, we're at 1, so that's halfway through this thing. And then we're negative 0.6 here, so about there. At pi, we get back to 0. So right there. Of course, you know that this is a cyclic curve. So from here, we're going to head up, and I am going to draw another full cycle back here so that we can get the picture of it. It's going to do that thing. The rest of this one would come from the negative and join up. Okay, so we kind of have a repeated pattern. Good. Let's talk a little bit about the characteristics of the tangent wave. The period is pi radians this time. Its y-intercept is 0. It crosses the y-axis just that one time at 0, but it has x-intercepts at every multiple of pi. Okay? Every multiple of pi, so pi n are x-intercepts. The domain is not all real numbers because multiples of pi halves are excluded. So x cannot equal any multiple of pi halves, any multiple of pi halves. The range on this function is, well, it can go from negative infinity to infinity. So the domain and range criteria are way different for this than for sine and cosine. Maximum and minimums do not apply. They're not applicable here because you can go as low as you want and as high as you want. But what is true is that there are vertical asymptotes at every multiple of pi halves. So at pi halves times n, there are vertical asymptotes. And that's our tangent function. Let's come in tomorrow ready to graph some trig functions. Get out there and do that trig, please.